Hello class. We are now going to jump into the topic of factoring quadratic functions when a is greater than 1. And this is the case where we cannot factor out a greatest common factor. These are quadratic functions where the a value is greater than 1 and there's no way to change that. And so we had to figure out, how do we factor a quadratic function when a is greater than 1? Well, the process is a little different. We're still going to look for g and h values, but instead of finding a g and an h value that will pretty much solve our problem. Remember, we're looking for two binomials where the product of those two binomials equal the quadratic function that we're looking for, and all we had to do was find a g and h for those two binomials, and that would give us the factors. In this case, we're going to look for g and h, but the g and h will give us information that we can use to rewrite our quadratic function, sort of break it up into two parts. And after we break the quadratic function up into two parts, we're going to group it a little differently, and we're going to factor out some numbers that will then allow us to do what we call a reverse distributive method, which will allow us to arrive at two binomials that represent our quadratic function. So I know I said a lot there. The example that I have here will just sort of bring that discussion together, but I was just trying to give you a big picture of how this is different from what we had been doing. We're still going to need to look for a g and h, and in some cases, we may need to use the quadratic function factoring worksheet to find that g and h. But when we find that g and h, we're going to use that g and h to rewrite our quadratic function and sort of group it differently. And once it's grouped differently, then we can pull some things out of the equation, which will allow us to do a reverse distributive method that will basically give us the two binomial expressions that we want, which is sort of like factoring our original quadratic function. So let's jump into this and sort of see what this means. So if we go to the top here, basically what this is saying is that when a is greater than 1, instead of using the process that we had been using, we're going to use what's called a reverse distributive method to come up with our two binomial expressions, such that when you multiply them together, they give us the quadratic function that we started off with. So in general, this is how the rules are different when a is greater than 1. So when a is greater than 1, and we're looking for our original g and h values, in this case, instead of the product of g and h equaling just c by itself, now what we want is the product of g and h to equal a times c. So whatever the a value is on the quadratic function times whatever the c value is, those are going to equal the product of g and h. The other criteria stays the same. we still will want the sum of G and H to equal B. Once we get the values of G and H, which do two things, where the sum of G and H is equal to B and the product of G and H is equal to A times C, then we'll want to rewrite our quadratic function using those values of G and H that we found that satisfied these two conditions. And what I mean by that is our original equation is ax squared plus bx plus c. What we want to do is take ax squared and put it to the left, take c and put it to the right, and then whatever we find that G and H are equal to, we want to put that G and H between ax squared and c and create a new equation that groups the quadratic function with these new values of gx and hx, which are going to replace b. Once we do this, we'll be able to reorganize our equation, and we'll be able to use the distributive method, the reverse distributive method, to come up with our two binomial expressions. So this example will show how we do that. This is just a general description of the process, so let's go down here to our example and just see how this works. Actually, once you see how this works, it's really pretty simple, but I must admit, until you actually see what's happening, it looks a little complex, but it's not quite that bad once we get through it. So our equation is 2x squared plus 11x plus 12. And you can see we've got a is greater than 1, it's 2, and there's no way we can factor out 2 from this equation, because in order to factor out 2, we would need to be able to evenly divide every term by 2. And you can see we could divide 12 by 2, but we can't divide 11 evenly by 2. So therefore this equation has to stay the way it is, and we have to find a way to factor it with this 2 greater than 1. So our first criteria, we need to find factors of AC we need to find factors of AC where the product of AC is equal to the product of GH, and where the sum of GH is equal to B. So let's look at what those numbers look like. AC, where A is equal to 2 and C is equal to 12, AC is equal to 24. And therefore, we need to find factors of 24 which are equal to the product of G and H, and that same G and H, the sum of G and H, has to equal to 11, because 11 is the value of B. Okay? So when we go to our quadratic function factoring spreadsheet, we see that the values of G equal 8 and H equals 3 satisfy that condition. 3 times 8 is equal to 24, and then 3 plus 8 equals 11. That's something you probably could have done in your head. You know, what value of 24, what is the product of two numbers that would give you 24, and the sum of those numbers would give you 11. Later on we'll have some much larger numbers, but in this example you probably could have did that in your head. But again, these are the numbers, G equals 8 and H equals 3. Now when we had A equals 1, this normally would have been the solution. It would have just been x plus 8 and x plus 3. So that would have been our solution. But since here we have a greater than 1, we have to go through a different process. And so what we have to do now is take this g equals 8 and h equals 3, and we're going to add an x to them and put them right in between ax squared and c. They're going to sort of represent our b cut into two different pieces. Because when you think about it, our b here is 11x, and what we have here is gx, which is going to be 8x, and hx, which is 3x. So we're really just taking that 11x and breaking it up into two pieces. And so that's what we do here. So you can see it's basically the same equation. 2x squared plus 8x plus 3x equals 12, where 8x plus 3x is really 11x. So we really have the same function, but now we've broken it up into two pieces, and this will allow us to group them differently. So as you see, when we come down here, what we do is we want to take this, we either want to take this 8x and associate it with the 2x squared, or we want to take the 8x and associate it with the 12. Conversely, we want to take the 3x and associate it with the 12, or take the 3x and associate it with the 2. Okay, and in this case, what we're going to do is take the 8x and associate it with the 12. And we're going to take the 3x and associate it with the 2x squared. And we're going to put parentheses around them. So that really doesn't change the equation. It's just that we're grouping them in a way that's going to allow us to use the reverse distributive process to create two binomial expressions that are multiplied together. And so what we have here now is 2x squared plus 3x, and then we have 8x squared plus 12. Now what we want to do is see if we can pull something out of this equation and what we can pull out of this equation, so that everything that's left inside the parentheses looks the same for both of these parentheses. And so what you see is if we pull x out of this parentheses, what we have left is 2x plus 3. And if we pull 4 out of this parentheses, what we have left is 2x plus 3. And that's why when we decided initially, we said, okay, we've got 8x here and we got 3x here, and remember we got those from solving for g and h here. And we said, okay, we have these two. Which ones are we going to associate these two terms? Are we going to associate the 3x with 12, or are we going to associate the 3x with the 2x squared? And so we decided to associate the 3x with the 2x squared and the 8x with the 12. And the reason we did that is because we could see that if we group it this way, it would allow us to, when we put them inside the parentheses and factor out whatever we can factor out, we grouped them this way so that when we decided to say factor the x out here and factor the 4 out here, it's going to leave what's inside the parentheses the same in both of these terms. So that's the trick. When you have these two numbers and you're trying to decide where do you want to associate these numbers, that's the decision that you have to make. Is the decision was to group the 3x with the 2x squared and the 8x with the 12, because we would be able to pull something out of each of these, so that when we pulled it out, what's left behind in the parentheses would be the same. So for example, if we had decided to keep the 3x with 12 and had the 8x with the 2x squared, and if we found that when we tried to pull something out of them, what was remaining was not the same, then we would have had to just go back and switch. And so when you initially try this, you might have decided to say, let me put the 3x with 12 and let me put the 8x with the 2x squared. And what would have happened is you would have tried to pull out something from both of these, and what was remaining would not be the same. And so if that's the case, if you see that you had chose to put 3x here and 8x here, and when you tried to factor things out, and what was remaining after you factored it out was not the same, that should tell you, okay, well, let me go back and try to put 8x here and 3x here, and then when I factor it out, is it the same like you can see it was here? Then that lets you know that that's what you should do. And so you see, I've sort of color coded it. If you take this 8x and you take factor 4 out of here, that's like dividing each of these terms by 4. You get 2x here and you get 3. In this particular parentheses, if you factor out x, because this is 2x squared, that's going to leave you with x, you get 2x plus 3. And so now that we have the expression in this format, we can now use the reverse distributive method to turn this equation basically into this. What you see here is we have two terms that are alike. What we can do is factor those out, and you end up having this format. And you can see that here. Okay, so what we have here, you can sort of look at this reverse example of a reverse distributive method process. Here you can sort of see B in this equation is representative of 2x plus 3 and 2x plus 3. That's what the B's represent. And then M would represent x here. A would represent 4 here. Okay? And so what we could do is we could factor that B out so that B is basically being multiplied by what's remaining, which is M plus A. And so again, that's what we have here. You have to think of the B's, as being the same as the 2x plus 3. See, the B's are sort of multiplied by both M and A. And here M is like x, A is like 4. What we can do is we could pull that B out, as we did here, and multiply it times M plus A. So here we could pull the 2x plus 3 out and multiply it times x plus 4. And so you see, that's what we have here. So what you have to do is you have to look at that, look at this relationship, because it doesn't make sense at first when you look at it. But then when you look at it, you see, oh, okay, I see it now. Again, the B's here, represent the 2x plus 3. And the m represents the x. And the a represents the 4. Okay, and so what we do is we factor these b's out. And when you factor the b's out, it's being multiplied. It's being multiplied by the parentheses of m plus a. And so that's what we do here. Again, you know, the 2x plus 3 is like the b. It's being factored out. And once you factor it out, that b is being multiplied by what was left. The m plus a, the m plus b, that's sort of like the x plus 4. And that's the solution right there. 2x plus 3 times x plus 4. Now we can prove that. Remember, what we can do is if we multiply this 2x plus 3 times x plus 4, it should give us the equation that we originally started with, which is 2x squared plus 11x plus 12. So let's do that. We've got 2x plus 3 times x plus 4. And what we do is we start with this x and we multiply x times 2x. That gives us 2x squared. Then we multiply this x times 3. We cross over this way. That gives us 3x. Then we come over to this 4 and we cross multiply. 4 times 2x equals 8x. So we put that 8x there. Then we go up and multiply 4 times 3, and that's 12. Then we add the like terms. 3x and 8x is 11x. And voila, there we go. So we see this is not magic. We see this does give us exactly what we started with. And that's how it works. So let's look at another example here. Okay, here we have 4x squared minus 4x minus 3. And again, we cannot factor that 4 out, because if we could actually factor that 4 out, then we would be able to divide each of these terms evenly by 4. We can divide the b term by 4, but we can't divide the c term by 4 evenly, so we have to use the process of factoring using the reverse distributive method. So again, we start by trying to find a g and h value, but remember, this g and h value is just going to allow us to reorganize our equation so that we can get it in a form that will allow us to do the reverse distributive process. Remember what we used to do when we found the g and h. That g and h became the values for our binomials, where we had g plus x plus g and x plus h, and so the g and h would directly give us the binomials that we're looking for. In this case, we have to use the g and h to rewrite our quadratic function in a way that allows us to find those binomials using the reverse distributive method. So again, let's look at our a and c value, because now what we need to find is the product of a and c. We don't just want to see the c value, we need to multiply a times c, and the product of g and h has to equal a times c, and the sum of g and h must equal b. So in this case, a times c equals 4 times negative 3, which equals negative 12. B is equal to negative 4. So we need to find factors of g. We need to find factors of minus 12 such that the product of g and h equals minus 12, and that they sum to minus 4. Okay, so what values of g and h such that when you multiply them they're equal to minus 12, and when you sum them together they're equal to minus 4? Okay, so you can probably do this in your head. If we have a g equal to minus 6 and an h equal to 2, that will satisfy this condition, right? Because minus 6 times 2 is equal to minus 12, and when you add minus 6 plus 2 together, you get minus 4. Again, we didn't have to go to the quadratic function factoring worksheet for this, even though you could if you wanted to. But again, this g and h value are not the solutions like they are normally. What they do is allow us to break our b value up into two separate pieces. When our equation started off, our b value is minus 4x. Now we're going to convert our b value into two components, minus 6x and plus 2x. So basically we take the x squared portion of our quadratic function of 4x squared, we put it on the left. We take the c and put it on the right, minus 3. Then we put this minus 6x plus 2x in between them. And it's not really changing the equation because minus 6x plus 2x equals minus 4. So we still have the same equation, but it's being broken up in a way that's going to allow us to use the reverse distributive process to come up with what the product of our binomials are. So again, what we have to decide at this point is the minus 6x going to go with the minus 3, or is the minus 6x going to stay here with the 4x squared? We have to decide which one of these we want to group them with. And in this case, when I did this, I grouped the minus 6x with the 4x squared, and I kept the 2x with the minus 3. And the reason I did that was because I saw that if we factored a 2x out of this term, it would give us the same term that this has over here. Okay? Again, you might have decided to say, hey, I want 6x to be grouped with the minus 3, and I want the 2x to be grouped with the 4x squared. If you would have done that when you tried to do some factoring, you would not have gotten anything inside the parentheses that would have been the same for both of them. Okay, so again, that's how you make the decision. It's okay. You can start off either way. But what happens is when you try to factor out terms from each of these, and if what's remaining is not the same like this, then you just have to switch them. And once you switch them, you will find that when you factor something from this term and you factor something from this term, that you're going to get something inside the parentheses that is the same. And in this case, when we kept the 6x with the 4x squared and the 2x with the minus 3, we see the only thing we needed to factor from the 2x minus 3 is a 1, which means we really didn't have to factor anything, but just for illustrative purposes I put a 1 there. And if we factor out a 2x, what we get left is a 2x minus 3 here. Okay? And so again, we have the situation where we can use the reverse distributive method to come up with our two binomial expressions. Again, what you have to do is you look at this reverse binomial, this reverse distributive method example here. Again, the b's represent the 2x minus 3. The m represents 2x. The a represents 1. Okay? And what we can do is we can pull the b out and multiply it times m plus a. The same way here, we can pull the 2x minus 3 out like we did here, which leaves behind 2x plus 1. Okay? And so initially this seems kind of complex, but once you see how this works, it's actually, kind of fun. And it's not so bad. And it's really kind of quick once you see how to set that up. Okay? Again, just stare at it. It'll come to you. And again, we can prove that these two expressions are equal to our original expression for, where is it? 4x squared minus 4x minus 3, just by multiplying them together. So we get 2x minus 3 times 2x plus 1. We take the first term below it and go straight up. So that's 2x squared times 2x squared is 4x squared. Then we take again the first term and cross multiply. That'd be 2x squared minus 3, so that's a minus 6x. Now we come over here to this term. That'll be 1 times 2x, which gives us plus 2x, and then 1 times a minus 3 gives us minus 3. We add the like terms. 2x plus a minus 6x is a minus 4x, plus 2x minus 3 gives us our original equation. Okay, so all of the other problems, here's another sample problem that you can look at. And then all of the problems, let's see how many problems did I give you. I gave you 5 problems. So all of these 5 problems are just like the problems we've done previously. And what I've done here is I've left a question mark. You can see here a question mark in the places where you have to make a decision about what goes there. Okay, here, here, and here, 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 and here. All you have to do is just go back up to the examples where I actually have numbers there. And again, I do it this way. I have this verbiage so you can understand the context in which these numbers are being created, the language, and hopefully you'll get the philosophy and the reasoning behind what you're doing, as opposed to just trying to remember a procedure. Okay? And so each one of these, each of the 5 I've sort of laid out in that process. So after you do about 3 or 4 of them, you should get the rhythm of this, and it'll start getting fun instead of being like, geez. And again, you're not really having to do a bunch of writing. I've done the writing for you. You just have to come in and plug and chug and spend your time thinking and understanding. Okay? So that's it. As you're working on these at your seat, please let me know how I can assist you. I will still have a lecture on this, but hopefully you'll be able to use this video to be able to start and stop and go at your own pace. So, all right. Thank you. Look forward to seeing you soon. Take care.